Thank you, Chris. So my name is Biermann, and I used to make the joke that I'm a German pretending to be French, because it's 13 years now that I live in France, and since 10 years I'm at CPHT at École Polytechnique. I want to start by warmly thanking all the people who are responsible for me being here. So I greatly enjoy these 2 weeks. It's really nice to see this crowd of people interested in what we are doing, how to push forward, asking interesting questions, making us think again, making us prepare lectures, sometimes late in the night. So it's really nice atmosphere here. Thanks for making all this possible, and thanks for having me here. So yes, I want to get rid of you. No, not of you. I'm very happy that you are still here. I want to get rid of, well, LDA, double counting, and of you. That's, of course, an ambitious goal. We'll see how far we get into that, but that's the direction. And I will try to argue that, in principle at least, conceptually, combining many-body perturbation theory within the GW approximation, and you have had the nice lecture by Ferdi on GW, combining this with dynamical mean field theory, on which you had a couple of lectures, should, in principle, give you a chance to do that. So my roadmap, and we will have the lecture today for this and another lecture tomorrow, don't get scared by the long list, will be to give you a few more motivations. So what's wrong with what we are doing at the moment? Why bother and try to work even harder? You have worked so hard yesterday, right? Why do something more? I will come back to what I would call the representability point of view. So that is closely related to what Marcus showed you this morning, and also what Andy discussed more briefly in his talk yesterday. And then I will do a little bit part on the blackboard. So I will derive the series formula on the blackboard, give you the GW plus DMFT equations, show what this gives on the most simple model, just an extended Hubbard model, then get a little bit more realistic, and then come back to, let's say, real systems. That will be certainly the lecture tomorrow, with also the link to the constrained random phase approximation that Ferdi has shown you, and also questions that are still open in the field. So you will see it's a field which is still relatively young, and it's still a field certainly in its starting. So essentially, the works that exist until now, you can more or less still put them on one slide. So you will see that it's also a field where still hands are needed, and so we are welcoming people who are willing to dive into that direction. Okay, so for the people who have seen my conference talk, you saw these two, well, summary slides, GW versus DMFT. So you argue that, well, GW is nice because you have a first principles description of screening. DMFT is nice because you can do any correlation strength, even up to the multi-insulator. The inverse is not true. DMFT doesn't tell you anything about screening, and GW cannot do anything that a perturbative method cannot do. It is perturbative. So that was the second slide to tell you, okay, let's combine the two, then we have twice screen, and that's fine. So for a conference talk, that's fine. You're motivated for the next 20 minutes, but now you have to be motivated for the next 2 hours. So I have to give you a little bit more explanations on this. Okay, let me divide this into 2 parts. Let me give you the motivations for the people who are GW aficionados. So you come from the electronic structure side, and you've learned about GW. Why would you like to combine it with DMFT? Well, actually, this slide could be very brief, because Ferdi had a lot of criticism on the GW already. He showed you all that is going wrong there. And in particular, it boils down, indeed, to saying that GW is not fit for the strong coupling limit. I want to add 2 remarks here. Because if you look in the literature, you get the feeling that GW is a method that essentially allows you to, I'm caricaturing a bit, to correct the band gap in silicon. You know, the Concham band gap is too small, you do GW, you get a shift up, and then it's corrected, and that's nice. However, reducing it to that, it's not doing really justice to the method, because it is using the method as an effective, improved one-particle picture. Essentially, you are just linearizing, in some sense, the self-energy at the end of your GW calculation. And that means you're adding some corrective potential to your quantum potential, but you're not using the method as a many-body method. In principle, GW, as Ferdi has shown you, has dynamical effects, has imaginary parts of the self-energy, has lifetime effects. So it is a many-body method, doesn't boil down to a one-particle picture. Nevertheless, it's often used in that way. So often people argue then, well, okay, it's used in that way, but if we use it in the true sense as a many-body method, then it should be able to describe strong correlations. Well, Ferdi has shown you that this is not the case. Even if you use GW properly with a full self-energy, you will not go to the strong coupling limit. You will not, for example, describe a Mott insulator. Again, let me go back to the literature. Sometimes you see the statement, well, we can apply it to magnetic materials, get them insulating. What do you say to that? Actually, you should answer that question now. Does that mean that GW can describe a Mott insulator? No. So you have seen the arguments that kind of shifting away bands by applying different self-energies to up and down spins stays within the band picture, but is not describing the Mott physics. So let's add these 2 points to the statement that GW is not suitable for the strong coupling limit, not suitable for describing Mott insulators. Finally, Ferdi has also shown you that there's questions about starting points, self-consistencies in GW. It's not necessarily a good idea, at least not for spectral properties, to do self-consistent GW calculations. That means, in principle, the method depends on the starting point, and I think for many GW people, this might be another convincing argument to actually try to go further. And last but not least, I want to add another one. What about finite temperatures? Well, again, in the literature, most of the calculations are done at 0 temperature, if you look at GW calculations. Nevertheless, it's not a principal restriction. You have, in principle, the possibility in GW calculations to do finite temperature calculations. But the temperature dependence, in general, will be rather trivial because precisely of the limitation that you're in a weak coupling regime. So you might also have the idea that you want to go to a finite temperature description of more strongly correlated materials here. Okay, now let me switch to the other side. And now let me talk to the DMFT people. Well, Antoine has called it a happy marriage, electronic structure theory with dynamical mean field theory. And I would like to reinvestigate a little bit the happy marriage and see where we can make it even happier. And for this, we have to go back and just think again, what are we really doing when we combine DMFT with electronic structure within density functional theory, within the local density approximation, or its generalized gradient approximations. So what are you doing there? And here I give you really the simplest version. So I'm skipping all the, let's say, fancy implementation details that Markus has shown you. I'm not talking about projectors, Wannier function, and so on. I'm just viewing it as a solution of a multi-orbital Hubbard Hamiltonian. So that does not correspond to the most fancy implementations, but it's entirely sufficient to make the points that I want to make on this issue. So what are you doing there? Well, you calculate the LDA Hamiltonian, express it in some localized basis set. So here I would be atomic size, m some orbital index, sigma the spin. And then you say, okay, that's my one-body Hamiltonian, really. Well, it's not completely true. I have to subtract something. So that's the famous double counting. So now it's something which is supposed to not have the interactions for some correlated subsets of orbitals anymore. And for those, I explicitly add many body terms here. So you have a choice now to have this, for example, run over correlated orbitals only, and this about some more, or whatever. But the essence is you add essentially Hubbard or Hubbard and Hund terms for orbitals that you have identified as correlated. And then you take this Hamiltonian and solve it with the refined many-body techniques that you have learned about in this school, namely in this case, dynamical mean field theory. And that's what we call LDA plus DMFT, most simple version. Okay, let me summarize. So what do? Construct multi-orbital Hubbard Hamiltonian by taking the one-body part from LDA or your favorite other functional GGA, whatever, expressed in a choice of localized orbitals. You add Hubbard and Hund interactions, you subtract the double counting, and you solve it with dynamical mean field theory. And of course, most important part here. Okay, now let's step back. What the hell are we really doing here? Construct a multi-orbital Hubbard Hamiltonian. Why Hubbard? Who has asked the question? Well, you had all these lectures and nobody jumped up, said, Coulomb interactions are long range. Why can I truncate? Why can I just keep the local part? Is it clear that I can get away with a Hubbard Hamiltonian, just keeping the local matrix element of the interaction? Well, you can ask the question for the second line. One body part from density functional theory. Why from density functional theory? Who is telling you that parametrizing Kohn-Sham states of density functional theory, Kohn-Sham band structures, is a good starting point for many-body theory? And actually, that point is closely related, you will realize here, to what you discussed with Andy Millis, for example, who showed you that, well, we don't actually know in the transition metal oxide where the oxygens are lying. You can choose your double counting, such that more or less, after the many-body correction, you put back the oxygens to the place where they were in DFT, in the Kohn-Sham states. But do you really want this? They may not be there. So is the starting point, the Kohn-Sham Hamiltonian, the best one that you could think of? Keep in mind that, let's assume you were reducing your U now. So you go back to an uncorrelated situation. Your result would reduce to that Hamiltonian that you put as a one-body part, right? So I like the example of strontium titanate, which is just one on the left to the one that you calculate in the tutorial, strontium vanadate. So it has 0 d electrons. So treat strontium titanate in LDA plus DMFT with U going to 0. It's not strongly correlated, so U going to 0. So you will recover the LDA band structure. That underestimates the band gap by 1.5 eV. So do you want LDA band structures as the starting point? Well, choose localized orbitals. How do we choose them? Is it equivalent to choose different windows? What is the best choice of orbitals? Add Hubbard and Hund interactions, but what is the value? How large should they be? Okay, so now Ferdi gave you a lecture about CRPA, telling you that we can actually calculate them. So to some extent, we have maybe solved that issue. But at the same time, he brought up another very important one, namely, by calculating them, he also showed that in principle, these interactions, as calculated from the constraint random phase approximation, are frequency dependent, are dynamical. And finally, I think I don't have to comment much more about the double counting. First of all, we said we are not sure we want to go back really to the position of the LDA states. But even if we wanted, it is not entirely clear how to do that really. And that is related to the fact that density functional theory, as you know and as the name says, is based on a description on terms of the density. Many body techniques naturally work with Green's functions. So you are using two different languages that do not have a natural match. Well, they do not have a natural match in the following sense. I can decide on orbitals that are correlated. I define a Green's function for that. But I can hardly tell you what was the contribution of those orbitals to the exchange correlation energy of density functional theory. So conceptually, it seems to me that it's really not possible to strictly mathematically subtract what you add. Okay, so subtract the double counting corrections. How? Solve within DMFT. Now we can ask an additional question. DMFT is assuming a local self-energy or approximating things as a local self-energy. What about K-dependence? And, well, I put a question mark even here. Even though my talk is not meant to tell you that LDA plus DMFT is bad. LDA plus DMFT is an excellent method to my taste. It was remarkably successful. You have a whole literature of materials that have been explored with that method. But what I'm arguing here is that it's worthwhile to think about these issues and to stay critical. Where are the weak points of our scheme? Okay, so the main point I want to make here is, as I alluded to already, that density functional theory is based on the description in terms of the density, while many body techniques naturally work with Green's functions. That is one point to motivate to try to get rid of density functional theory to replace it by a Green's function method. And that is actually just a caricature way of illustrating what I just said, how to match these descriptions, knowing that the exchange correlation energy is by no means linear in the different orbital contributions. So you cannot just say this comes from my D states and I subtract it and I replace it. Okay, so first argument, happiness of marriage is at least not guaranteed due to the fact that there's this mismatch of density and Green's function. But there's a second point, namely the one that we alluded to essentially in the first line on the slide before. DMFT knows only about a Hubbard U, possibly a Hund's J. Density functional theory works in the continuum. It knows about the Coulomb interaction. Coulomb interaction really as a 1 over r minus r prime operator. So now, let's take a little poll here. If I compare U, typical values used for DMFT, with matrix elements of this operator here in the same orbitals, what's your opinion about the ratios? I take guesses. Yes? Okay, so you're saying the matrix element of this operator should be larger than the U. And indeed, you paid attention in Farade's lecture, this thing is an unscreened interaction, and this is a partially screened one. So that should be much larger. How much? Who thinks that it's like twice? Who thinks that it's like 1,000 times larger? Okay, Ferdi, you were very successful. Who thinks that it's about an order of magnitude bigger? Yeah, okay, you were kind of successful. Okay. So I stole this slide from Ferdi. Actually, I'm not sure it was exactly that slide, but more or less. So that was for strontium vanadate, your favorite, the frequency-dependent interaction. And you see it goes from a screened value or partially screened value for the calculation of U to an unscreened value here. And what I'm just arguing here is that the two numbers that I have been asking you is the U value here, the static screened, well, partially screened Coulomb interaction of the order of 3, 4 eV, and that this here, at high frequencies, where screening is not efficient anymore, corresponds actually to the bare matrix element of the Coulomb interaction. Really the matrix element of 1 over r minus r prime. And you see that, indeed, here, while 3, 4 eV, 25, you have more or less an order of magnitude. So there's this kind of mismatch. DMFT knows only about the 3 eV, but the density function Hamiltonian was calculated with this knowledge of the full interaction. So the question you can really ask, how do you bridge in these two descriptions? How do you get from 1 over r Coulomb interaction to a description as plus U? So now I should probably pause 1 second and be a little bit more critical to my question about why do we take the Hubbard model? Does anybody want to make a comment on that? Well, probably because many people of you believe that in a more or less mathematical sense, if you think of a renormalization group treatment starting from a high energy Hamiltonian, going down to lower energy scales, the relevant interaction will be the local part. So you think that actually your physics will be described by an effective model where the relevant degrees of freedom are actually described within these local interactions. However, that is a quite conceptual argument, and nobody has ever started from a full Coulomb Hamiltonian and done mathematically this kind of downfolding of the interaction explicitly. That would be needed to really link the parameters of a low energy model to your initial Coulomb Hamiltonian. So the question I'm asking here, can we really do this kind of downfolding in some way? Of course, this has to involve some approximations, but can we in some way bridge these mismatch of energy scales? Okay, so now we have raised high expectations, and I warn you, you will not have the answers to everything here I put up. I'm just making you start to think about it. So we want to work entirely with Green's functions. We really want to get rid of a description in terms of the density. Let it be as nice as it is, and let it be as successful as it is for all the total energy calculations that we have seen in the literature that you're probably doing and that will still come. In this context here, we want to get rid of it and just stick to Green's functions. Then we want to have the link explicitly to the Coulomb interactions in the continuum. Somehow, this 1 over r minus r prime should show up. And finally, we don't want to do GW, because if you just ask for this here, then we are back to doing the GW approximation. But we don't want to stick to that, because we want to have something which is fit also to go to the strong coupling limit. Are there remarks, questions so far? Is it okay? Too easy? No? Okay. Okay, so that means we really want to try to make this a happy marriage with the arguments you had before and working in a Green's function language. Well, and actually, GW here works not only with a Green's function, it also works with W. What about DMFT? Well, DMFT works in Green's function language, but what about W? Can you make DMFT work also with W? Okay, so this brings me to a very short reminder of what you have seen yesterday and this morning, namely to, let's say, a view of, a kind of viewing things that I would call the representability point of view. So Marcus this morning has argued very nicely that you can always view things as having a physical quantity represented by some auxiliary system. You can do that. For example, I will pick the example here of density function theory, where you want to represent a physical quantity, which is the density of your system, within a simplified system, a simpler system, so to say, which is a non-interacting system, your Conchem system. And the only purpose of this Conchem system is to reproduce the physical density. So now, a non-interacting system, if you don't do anything special, will not give you the density you want. So you have to do something. You have to put the right effective potential, which produces precisely that density, and that is the Conchem potential. So you choose the Conchem potential in such a way that you get the physical density, and that is why things in density functional theory are functionals of the density. So now you have seen with Marcus that essentially the same is true for DMFT. You can ask the question, can I represent the local part of the physical Green's function of my system within a simpler quantum many-body system? And this simpler quantum many-body system will be a purely local one. Will be an Anderson impurity model that you have seen so nicely how to solve, for example, in Thomas' lectures, in other lectures, Michel, Marcus, and so on. So a local problem, even if it's fully non-interacting, is much easier to solve than the initial full problem. So same philosophy here. Can we represent the local Green's function of your physical system as a solution of some auxiliary, in this case, local impurity problem? And now you can ask the question, can we extend that philosophy? Okay, so that is just this same philosophy, just resuming once more. So assume we know the local Green's function somehow, whatever, by some miracle, somebody gave it to me. I asked the question, can I find a quantum impurity problem such that the solution of that quantum impurity problem, the Green's function of the impurity, is equal to that local thing? So that means, can I construct an effective atom such that the Green's function of that effective atom is the local part of the Green's function of my real solid? And you have seen in the mathematical language that Marcus has shown you this morning that you can do that by putting some bath here. So that is, again, analogous to, for the people who know DFT better, put the right Cohen potential in order to produce the full interacting density within a non-interacting system. Here, put the right bath to produce the local part of the Green's function of that solid within that effective atom problem. So now let me ask the next question. Assume we know not only the local part of the Green's function of my solid, but that I also know the local part of the screen-Coulomb interaction, the W that Ferdi introduced to you. Can we still construct a quantum impurity problem such that we reproduce now both quantities? So what would you think what you should do in this extended dynamical mean field theory here? Any ideas? Yes?
Take both as a parameter, not separately.
Yeah, okay. So you want to have two parameters?
No.
No.
One parameter which is either G plus W or W within G.
Oh, G plus W. No, be careful. Because G is a fermionic Green's function. W is not. And W, actually, I will argue later that it is even worse. It's a bosonic Green's function to some extent. So you cannot just add the two. It's a nice try, but mathematically, I have a conceptual problem with that. Product. Well, GW, then you're back to 30. You have sigma, right? How do you construct then an impurity problem? Well, but I thought I heard actually some answer that I liked, because to reproduce the Green's function, the G log, you need some effective bath, and you have to adjust that bath in an effective way, right? So now you have a second quantity that you want to represent. So just put a second parameter, well, not parameter, but a second function to determine, right? I need more degrees of freedom to have both. So let me put something, and now I think you will say, oh yes, of course. Let's put a function here that I will call dynamical U. Let's put some interaction that I will not consider as externally given for my model, but that I will also determine in some way self-consistently in order to make this problem such that it will reproduce both of those, local Green's function and local Coulomb interaction. And of course, I will have to tell you how this construction works. But from a conceptual point of view, this seems to be something like a bare interaction of this atom, and then it will produce a screened interaction, and then we'll just have to adjust this bare one in order to have the screened one. Okay, so that means mathematically what I want to do is to work actually again in a functional formalism. But I want to work in a functional formalism where I construct a functional both of the Green's function of the solid and a second quantity, which is the screened Coulomb interaction W. So you have seen functionals of magnetization for the Ising model, of density for density functional theory, and this morning Marcus discussed DMFT from the point of view of the Latinger-Watt functional, so a functional of G. Now I want to extend this to a functional of G and W. And that has actually been realized, or it was argued here in this paper that it was possible and even constructed by Almblatt et al. In 1999. So, function of two quantities, and okay, I will follow a strategy which is similar to the one that Markus showed you. I want to construct this functional as being actually the free energy of your system, and completely analogous to what he showed you, I want to argue that there's a trivial part, which is just something like the Hartree contribution, and then there's the rest. The rest containing all interesting physics, all correlations, and so on. Again, viewed in analogy to the Kohn-Sham construction, you have the trivial parts, and then you put all the rest into some effective exchange correlation potential, and that's the hard part to calculate or approximate. Okay, let me do one or two slides more just to make sure that we are talking about the same things. So you have seen Green's functions extensively in the lectures by Vijay. So one particle propagator really here, looking at what happens to a particle that I create in the system at some point, at some time 0, and then try to destroy at some later time tau. And you have discussed that this has links to the spectral function. Here I have written it in the K-resolved version, namely by taking the imaginary part of this thing. Okay, and final remark before I switch to the blackboard. I already alluded to that W will kind of acquire an additional interpretation in the following. Namely, you have seen it in Ferdi's lecture as being the screened interaction, defined, for example, here as the bare Coulomb interaction screened by a dielectric tensor, or the thing expressed by the polarization that Ferdi showed you. I will introduce this first a little bit differently, namely as a propagator of bosons. I will show you what this means in a minute, and then show you that it has still the physically intuitive interpretation that you were assuming. Okay, so now I would like to come to more pedestrian ways of proceeding. And for this, yes, thank you very much. Are there questions, remarks, comments, suggestions, complaints so far? You are bearing with me? Okay. And I heard that I should start writing here. What is this part is good? Okay. Okay, so let me start by fixing my notations. Oh no, actually let me start by, well, okay, you had already the, oops, the references. So yet another one. But I think this will be the last one for this school that you have to derive as functional. So let me give credit again to Almblatt et al. And I add, though, that the derivation in this paper is nice, but I find it a little bit hard to read. So the one that I give you here is one that we put in some proceedings in 2004, actually, with Ferdi and Antoine, and that you can just download from arXiv. So that's their arXiv in 2004. I don't have the exact number. Okay, so then let me start by fixing my notations. So I will work quite generically with a many-body Hamiltonian that I separate into the interesting part, the interaction part, and the one-body part. But I will put in the interaction part somehow the interactions beyond Hartree. So that means I will write something like this, where I look at the fluctuations of, so I'm throwing some chalk here. Yeah, okay, thanks. Okay. Yeah, now I wanted not to flatten everything here. So thanks. Okay, so what I did here is to define my delta n as the density operator from which I subtract the mean value. So that means essentially that the hard tree terms are going here. It's just a question of notation because I don't want to bother with them anymore. And so that means this is actually the field operators minus precisely this average. Okay, and that means that as I said, the non-interacting part has not only the kinetic energy, the part associated to your external potential, for example, the ionic potential of your solid, but also the hard tree contributions. Okay, so again now, wanted. Wanted is a free energy functional, the free energy of the solid, expressed as a functional of G and W. Oops. Okay. And I will be a bit lazy, namely, I will put all interesting or uninteresting physical constants to 1. For example, I will not care about beta. I will probably make lots of sign mistakes. Factors of 2 and 1/2 are homework to put correctly. So let me put beta equal 1, and let me write that my free energy is minus the log of the partition function. So I have eaten the kt here. So that means my partition function, okay, let me write this here. The partition function, as you learned in the lectures by Vijay, you can write as a fermionic path integral. So I will do that schematically. That's another laziness. I will be very symbolic in my notations in order to avoid all the integrals and indices. You will see in a second what I mean by that. And I will write that actually my partition function is a Grassmann integral here, fermionic path integral, exponential, some action, and I will give you the action in a second. I will put it down here. This action is just the one-body part. I will do it in Matsubara frequencies here, minus the one-body Hamiltonian that I defined there, psi, plus the interaction part. And now you see what I mean by symbolic notation. Oops. So essentially, I will say that if I write an integral like this, what you should read actually is that it's an integration here, and then here you have the sum over Matsubara frequencies, and so on. It looks a little bit lazy, but you will see in the formulas that come that it greatly simplifies the global view on the question. So I don't want to bother with indices. I want to give you just the physical picture of this construction. Okay, so now what do you do with this thing? Any suggestions? You have a nasty interacting many-body system here, right? I think Vijay gave you actually some strategies that you could use now. How about Satunovic? Good. Okay. So what does it mean? So I want to rewrite this interacting part. I want to rewrite this quartic part. And I want to rewrite in a way that I introduce some fluctuating field, some auxiliary field to discouple that. And then I have a non-interacting Hamiltonian plus this field. And I have to, that's the price, integrate over all field configurations with some weight. Okay, the mathematical way to do that, so you studied that, I think, in great detail even before I arrived, right? That is to rewrite, and now I need a little bit more chalk here still. Yes. Okay, let me get these books here. So let me rewrite that. Oops. Oops, yeah, sorry. Okay. So look at this. Why is this useful? Well, because that was the term that I want to rewrite here. Phi is my auxiliary field that I introduced to decouple. It comes with the weight given here by the interaction. And here you see that my notation is really symbolic because V was the full long-range Coulomb interaction. So to write it as an operator -1 like this, you should make careful treatments, for example, go to Fourier space and so on. However, I just keep it in this symbolic way. So phi is the fluctuating field, and it couples to the density. And then you have a term here, which is quadratic. And if I write now a Gaussian integral, we'll just go into some renormalization constant, into some normalization constant. So that means, using this, I can write that exponential -1/2 V delta n. The interesting part here in the action is actually integral over my field exponential -1/2 the weight term here and the coupling to the field. So now I think I can still do one line, but it's better I do it on that side. Well, while I erase, and French professors are used to that, you can already take this expression and plug it into the thing here. Sorry, Thomas. Okay. So that means exponential -s can be rewritten as as integral over the parts with the one-body Green's function. Sorry, I think I didn't introduce that definition here. With I or without I, depending on if you're in Matsubara space. And then precisely the term with the fluctuating field, coupling to the density, and the weight term. Okay, I should not have written it there. The weight term exponential -1/2. And the whole thing integrated over all configurations of the field. Okay, that looks not too bad. That is a problem that, okay, apart from this fluctuating field here, well, is Gaussian on this side, just that, then I have the field integration to do afterwards. What am I going to do with this now? Well, I told you in the beginning, a whole song and dance, that this is in order to construct a functional of G and W. You have not seen this yet here. And also, we should use the techniques that Marcus introduced this morning. Namely, you learned that coupling constants can be useful. So let's do both. Do we have some colored chalk here? Yes. Let me just introduce some alpha here. And you will agree that the physical case will be alpha equal 1. Okay. Nothing changed so far. As soon as I put alpha equal 1, I'm back to the original thing. Secondly, I will add source terms. I will do exactly what Marcus has taught you this morning, namely that you can do Lagrange multipliers with source terms imposing a certain value to expectation values of some quantities. So I will do that by multiplying by two terms. I will add a source coupling to the fermionic field here, and that thing I will call suggestively sigma. This is not a sum here, but it's generally a sigma. That's the name for my source term here. And I will do that also for the decoupling field. So I will aim at both constraining eventually the expectation values of propagators of the fermions and this field here. I will call it a bosonic field. It doesn't have fermion statistics, just some number that you can view as a bosonic field. And I will do my construction, yes, in the way that I will be able to constrain these expectation values. Yes?
Why shouldn't the alpha be also on the right term? Because you put the alpha on the interaction V delta n delta n, and not specifically on each term.
At the moment, you can do anything with alpha. You will see in a page or so that this choice of alpha is not stupid. But at the moment, I have not changed anything. I've just put alpha, and alpha equal 1 is the physical system for the moment.
But V is already there in another term.
Yes, yes, yes. I don't care.
So alpha equal to 0 should not lead to something which does not have V.
Okay, well, you will see in a second. I come to alpha equals 0. You are jumping a little bit ahead, yes. But let me continue step by step. Okay, let me realize now that what I have done actually is that I have written my free energy, which has suddenly become a functional of my source terms, sigma and p, in a way, this chalk is not very nice, in a way where I have an integral over all the Grassmann fields, an integral over the bosonic field, and then some action that I call S of sigma and p that I will still squeeze in here. That has the trivial parts corresponding to the Hartree, the field coupling to the density, and then the source terms for both fermions and bosons, and not to forget also the weight factor. Okay, who agrees on that? Oh, okay. Write it down, have a look, and then complain, please. I did nothing, actually, so just make sure you see what I'm doing. Okay, so who agrees now?
You have not bothered to keep the expectation value of psi dagger psi to which you want to constrain it?
Yes, yes. So I've just added this, and you will see that, so it's actually the same thing, but you will see that this is sufficient, yes. Other questions, remarks? Who agrees that this is correct so far? Oh, they're all suspecting that there's a catch here. I'm just trying to see if you're still awake. Okay. Other questions? Shall I continue? Yes? Okay. Okay, let me look what happens if I take the derivative of this functional with respect to its two arguments. So let me do DFT sigma, and let me do that actually with a minus sign. Who can tell me what is the result of this? Good. So the answer that was here was the expectation value of the fermionic field here, psi dagger psi. Because if I derive this, of course, the log will give me the partition function in the denominator to normalize, and then I will have a functional integral where I get precisely the thing here. So that means I will say that this is, okay, up to sines possibly, G itself. What happens if I take, in this case, twice df dp? Okay, same argument. You will get this down. Normalization works again. And that means I will have the expectation value of phi phi here. And I will give a new name to that. I haven't used the letter W yet, have I? So let's call this beast here W, and you will see later on that that corresponds actually to what you physically assume to be W, namely the screen Coulomb interaction. I've on purpose defined it here differently. I define it as the bosonic propagator, and you will see that this acquires afterwards the role of a screen Coulomb interaction.
Excuse me. This epsilon and p are dependent on tau minus tau prime in general, is it?
Sorry, what is dependent on?
The sigma and p are dependent on tau and tau prime.
Yes,
Okay.
yes, absolutely. And at this stage, even r prime, t, all kinds of variables you want. Yeah. Okay, so now let me go ahead and let me do the Legendre transformation. So I'm really grateful to Marcus that he has introduced all this formalism so nicely this morning. So you have now a functional of G and W, where I use these relations to eliminate the dependence on sigma and p. So let me write the thing, and let's then have a look. So I take the original functional f, and I subtract, as in a good Legendre transformation, the derivative part times this thing. And now I need more space. Minus the same thing for the part with the derivative with respect to p. Okay, but now, what can you tell me? The FD sigma, that's minus G, right? The FDP here, that's half of W. So now, what I have to do is, by inversion of these relations, express this one, which was a functional of sigma and p, and the sigma and the p that I have here, by expressions of G and W, and then I have my functional of G and W. So that's the analog of what you have seen this morning. I'm constructing something where I want to fix the Green's function and the screen Coulomb interaction, and I ask, with which sources do I do that? So I'm constructing a machinery which allows me to control those variables that I want to control. Think of density functional theory again. You want to impose the density. You put the corresponding Cohen-Shem potential.
Just one, when we are evaluating those functional derivatives, we are putting the source term equal to 0?
Okay. You want me to evaluate the functional derivatives, yes? Actually, no, I want to write for you one thing first. Wait, okay, let me first make one remark still for the analogy to what Marcus said with trivial part and non-trivial part, so the simple part corresponding to Hartree and the rest. So what do you think if I pretend to be at the same time cone and sham, I want to make a separation of this functional into two parts, one which I know and one which I don't know. How would you do that? Can you calculate the functional in some case? Vijay is nodding, so you should give him an answer. Good, yes. So if I put alpha equal to 0, what happens? If I put alpha equal to 0, then I have eliminated the only term coupling fermions and bosons. So then I will only have this and this for the fermions, and this for the bosons. And that means I can actually, both are Gaussian, I can integrate out both, and I will have a simple expression. So let's write this down. And that means I will actually separate this thing into the mean field part, which is the one corresponding to alpha equal to 0, and the rest. And the rest, I will give it a new name because it will be important in the following. I will call this psi. And after all what Marcus did, you will not be surprised, and you can verify that by an immediate look, that indeed this is a mathematical identity, even though maybe not so much of use for practical purposes in the following. Yes, Tanushi? No. Alpha equal to 0 still has the Hartree parts here. Alpha equal to 0 is just the one where I don't have boson-fermion coupling, so I don't have any correlation effects. But it's not true that it's non-interacting in the sense of electronic structure, people. The Hartree part is there. Okay, so now you made this remark that for alpha equals 0, I can calculate the f, and let me do that here. So the f for alpha equals 0 will be the log of two factors, and this really factorizes so nicely, as we said, because, oops, sorry. Sorry, I'm a big user here. Because the fermions and the bosons do not couple anymore. So for the fermions, we have now the G0 part and the sigma. And for the 1/2. For the bosons, I have the part stemming from the weight, which was the V here, and the P part that I introduced here. Okay, so that means I have two Gaussian integrals to do, the log of this, and you can do that as a little exercise. You will just find that this is getting down, or you know it already, getting down this argument of the Gaussian here. Again, my signs and factors of 2 and 1/2 are probably all wrong. That's homework. So I don't guarantee for this. Okay, something like that. So now, can I express this as a functional of G and W? Knowing that G was minus DFT sigma. And now you can tell me G is minus DFT sigma. So that looks probably familiar to many people among you. Who knows that? Okay, good. There's people still awake. Then W, same story. Factor of 2 df dp. What do I get? Well, analogous thing. So we have chosen suggestive names here. We have not introduced them in the way you were used to them, but you see already where we are heading. We are heading towards a description where W is the bosonic propagator in analogy to the fermionic propagator G. The Baire-Green's function G for fermions corresponds to the Baire-Coulomb interaction here, and the self-energy for the bosons will be our polarization. So it will be very useful in the following to always think in these correspondences. We are just kind of doubling the DMFT loop, supplementing it by a second loop running over two particle quantities represented here in this bosonic way. Okay, so that means I have found now that my expression okay, time is running. That my expression for F for alpha equals 0 without coupling between the, sorry, that is gone. Minus 1/2 trace log W is just this here. And that also means that now we have actually derived the expression that Markus has just given you this morning, namely, if we supplement it with the terms from the Legendre transformation, trace G and sigma should now be expressed by G, so that means we will replace it by G minus 1 minus G minus 1. That was the sigma of the Legendre transformation, and minus 1/2 trace W times P, and P is V minus 1 minus W minus 1. That was the expression that Markus gave you this morning. Okay, and again, that was for alpha equals 0. The full functional will now be this thing supplemented by what I will call in the following the interesting part. Okay. Now let's look. We were introducing this gamma as a free energy functional that should be stationary for my physical solution. So let me look what stationarity of this functional means. So let me take precisely the last expression, so with both parts, and derive it. So that means I will have, oops, let me start with the d gamma dg, and what do you get? Sorry? Yes, okay. So you get G minus 1 minus G0 minus 1. But then let's not forget the interesting part here. So that I keep formally plus d psi dg. And indeed, you are telling me that means that actually d psi dg at stationarity is G0 minus 1 minus G minus 1 equals sigma. Analogously, d gamma dw, what do I expect? Well, you don't even have to make the calculation if you understood our analogies here. You know what we should put here. Well, up to the famous factors 1/2 and minus and so on. You will have the difference of w minus 1 and v minus 1 such that the derivative of psi with respect to w will be 1/2 v minus 1 minus w minus 1, and that's what we called p. So that means we have constructed the free energy functional in such a way that the stationarity of that functional is equivalent to saying that the functional derivatives of the psi functional that I was after correspond actually to the polarization and the self-energy of your system. Again, to the self-energy for the fermions and to the self-energy of the bosons. Here again you have this analogy. Okay, one more remark on W is in order now. Namely, I will not go through that, but you can do it as a not too hard exercise. You can show by taking the two expressions for the action with and without Hubbard-Satunowitz transformation that if you calculate the charge-charge correlation function, you can actually relate W to the to the Baire-Coulomb interaction by saying that here you have the charge-charge correlator. So that means something of this kind. And that is now my justification of getting back to Faraday's definition. So if this is true, then this means indeed that W is the screen-Coulomb interaction of your system. And that in turn means that P is the difference of the inverse of the Baire-Coulomb interaction and the screened one. And then you remember that Faraday also wrote something like this, where indeed P was the polarization. So that means what we introduced here very formally is indeed the polarization of my system. Okay, and the last formal remark, but this is just for aficionados, namely also the expression of the psi functional that we wrote as this integral over the coupling constant. You could show that, and I will not do this here, but it's not too hard to see, that indeed you can rewrite it as, again, a coupling constant integration over some expectation value, namely the one coupling bosons and fermions. And that's not a surprise, because that is precisely the term that was governing this coupling constant, and that's why I put it at this place. Okay, I think at this point I would like to switch back to the to the screen. Yes. And I'm very advanced in time, right? So I have 20 minutes. Is it true? Thank you. Okay, good. Okay, so this is just summarizing what we just did. We have constructed this free energy functional gamma here, where the alpha equals 0 part corresponds essentially to the trivial things, to Hartree, and everything interesting is here in the psi functional, which has the following properties, namely that its derivative with respect to G should give sigma, and the derivative with respect to W should give you the polarization. So now, I was insisting several times that the easy part we did, now comes the hard part. I did the easy part, now you calculate the other one. Do you think it's possible? So what are we going to do now? We are stuck? Okay, we cannot solve it completely, you're right. Because then we would have solved actually the many-body problem if we can do that. So we have to find approximations to write down explicit forms for the second part. What do you propose? Do you know many-body schemes? Yes, you have learned a lot about those, right? So let's make a little poll. What do we need to write as a psi functional in order to get the GW approximation? So in GW, this is why it's called GW, the self-energy is equal to GW, right? Or minus GW if you're in Matsubara. So you want something where, as a result, you get sigma equal minus GW. What about P? If you do GW, you calculate P in the RPA, essentially. You calculate the bubble, right? So P is GG. So now you need a functional such that if you calculate the polarization, you get P. How do you calculate the polarization from a functional? Well, that's not hidden. So d psi dW should be P, should be GG. d psi dG should be sigma equal minus GW. Any solution to that problem? Ah, good. GWG. So you derive with respect to G and you get GW. You derive with respect to W and you get GG. So if you want to have the GW approximation, you write this functional actually just to first order in W in the screen-Coulomb interaction. That's the expression, and everything else follows. That's maybe not the way you learn the GW approximation the first way, but that's a completely valid way to define things. Okay, for once I have written everything now with the indices, so you see that actually if you put this back, it becomes much more lengthy, so you understand why I skipped it. Now, the probably tougher question, what about the psi functional in DMFT? So if you're a DMFT person, how would you go about this psi functional? Well, Markus has shown you this morning how you go about if you just do usual DMFT if you have a functional of G, right? So he has argued. Exactly. So this morning you have argued that DMFT corresponds actually to restricting the functional to local Green's functions to write a phi local, so to say, phi impurity as a functional of the impurity Green's function. So let's do the same thing here. And probably have a few more slides. So this was the thing we discussed before. So now you understand the meaning of the cartoon I showed you here. You want to write a functional where you can calculate everything from an atom, G impurity and W impurity. And that means that you will actually construct the action of an impurity model and calculate everything from that action. And that corresponds to calculating everything from some hypothetical DMFT functional, well, not hypothetical actually, some local functional, which sums everything to all orders, but is exact. Okay, and then you know in DMFT you have a self-consistency condition. You have studied in detail how to determine the self-consistent path, which allows you to have the good Green's function. And now we will have to decide how to write a self-consistency such that also the second auxiliary quantity, the dynamical Hubbard-U, gets the right value in order to produce our W. Okay, writing this once in a functional way. So on a conceptual level, we have a impurity free energy as a functional of a local quantity that I call G-imp, another local quantity W-imp, with all the expressions we just derived, but everywhere G-imp replacing the Green's function, and the Weiss field, the non-interacting Green's function of the impurity model, replacing the non-interacting Green's function, the U here did, as a bare interaction of the impurity, replacing the bare interaction, and the simple part supplemented by the interesting part here, this being the correlation part of this functional. And when we calculate things, we calculate a local self-energy, a local Green's function, a local W from an impurity model. That means that we are actually calculating things such that these psi obeys to these relations. So that means you actually have a means to calculate this functional. I cannot write you down in an expression on the blackboard for psi, but we have a prescription how to calculate that. And we have the prescription how to, in principle, even calculate that, well, numerically exactly with the techniques, for example, that Philip will show you. Oops, okay. So now you have understood what GW is doing to that functional, and you have understood what DMFT, or actually extended DMFT, so this here refers really to the fact that I have the second loop around, is doing to this functional. Now we were saying we want to combine the two. We want to combine the best of two worlds. We want to combine the non-local description of the GW approximation with a good description of local physics to all orders of DMFT. How do you do that? Any proposals? So obviously that should work at the functional level, otherwise I wouldn't have spent an hour to put this up. So let's combine things at a functional level. So let's say that, okay, DMFT is nice for local quantities. Let's keep the DMFT description for everything that is local. But let's not stop there. Let's supplement it by a second part to this functional, which we calculate from GW. So let's take everything non-local from many-body perturbation theory to first order in W, so from the GW approximation, and the local part from DMFT. What do I mean by taking this from non-local GW? Well, that essentially means, or not essentially, this means that we define this part of the functional as being the GW functional that you just gave me, GWG, minus the local part of it. And now comes an interesting, nice accident, namely that the local part, okay, maybe I should write this one line on the blackboard. The local part, where do I have it here? No. Oh, actually, yes, okay. Can I switch back to the blackboard immediately? That will be the last time switching back and forth then. Okay, thanks. Okay, so what I just was saying is that the GW functional GWG has the nice property that if I look at its local part, and when I talk about local, I have to say what I mean by local. Let me for the moment imagine that I'm doing things on a lattice model, or that I'm in a solid, but I have defined a localized basis set, Wannier functions, projective, whatever you want, so that I have a notion of atomic sites, and that I can decide if a Green's function is living with its two indices on the same atomic site or not. So that's what I will call G local for the moment, so something which lives on the same atomic site here. And then you have the nice feature that the local part of this functional is actually just this functional evaluated for the local quantities. In other words, if you do the k-sums, so you project directly the product to the product, or you project the single factors of the product, that is the same thing. Okay, so that means my functional is well defined if I say that I take the local part from DMFT, from an impurity model, and I take the non-local one from GW, where psi GW non-local is nothing else than GWG minus the local part of this thing. Okay, and that is actually the only ad hoc assumption for the GW plus DMFT formalism. Because now you have a functional from which you can derive the full set of GW plus DMFT equations just by using the relations for self-energy and derivative of psi with respect to G and so on. Why I say?
Why do you say this state is ad hoc?
No, no. This thing is ad hoc. This is the thing, okay. Nobody tells me that the God-given psi functional has to look like that. But indeed, I agree with you, it's a reasonable assumption. Yeah. But of course, then you can argue if you need refinement. So I mean, I will come back to the limitations at the end. Yeah.
G non-local has things like G, R, W, R prime, and again G, R.
Wait, you're talking about G of a G.
So this
Yeah.
psi local is everything local. The one that you
This is everything local. Yes. Yes.
So the difference can have something local and something from different.
No, that's precisely the interesting thing. The indices are such that you have R prime, so you're not mixing local and non-local parts. That is precisely the nice thing and the origin of this accident. So if you go to higher orders, then it's not true, and then you're embarrassed to decide what to put in which part. Yes. That is precisely the thing, that this is indeed here equal to G log, W log, G log.
So there is a natural way to split this.
Exactly, exactly. At this order in perturbation theory, there's a natural way of splitting things. Yeah. Okay, so now let me see what we get for the equations. Okay, that is. Let me write this maybe here. Or I can leave this in. So while I erase, you can already start thinking how you would calculate things now. What should you take, for example, for the self-energy, for sigma? Okay, so what do we know? We know that sigma should be deep psi dg, right? So now my functional has these, let's say, 3 different parts. So I take these 3 different derivatives. Oh, what am I doing here? I take the one of the local part, and then I will have the one for the GW part. But you just calculated for me that if I derive that with respect to G, I will get the GW self-energy, right? So I will get GW. So let me write it like this because of this embarrassing minus sign. But essentially that's what it is. And then I have to subtract precisely that local part that we just discussed. So GW local, that means minus G log W log. But that looks interesting because this tells me that Ferdi gives me a self-energy. I cut one chunk off, namely the local part. I just throw it away. And I replace it with this thing. What is this? That is my impurity self-energy. This I have to calculate from an impurity model. And we will have to see which is the exact impurity model. That it means which are the self-consistency conditions associated with that. But this will come from the DMFT construction. So I'm really doing what we're planning to, namely take the best of both worlds, take GW, which is nice for everything non-local, throw away the local part, which is first order in W local, and we can do it better. This is to all orders. We replace it, and we have a better estimate. So let me do the same thing for the polarization. P was deep psi dW. And what do you get for that? Well, without surprise, you will get something which was the deep psi dW imp. I abbreviate a little bit the notation now. I directly tell you that this should be P imp for reasons that you probably see. And then I will add the P that I would have in GW, which is the GG. I call this the P RPA, so that is actually GG here. And from this I should subtract the same thing, but projected locally. So this thing will be something like G log G log. Okay. So that means, again here, I do the same manipulation. I start from the polarization that you would calculate in GW, or for the use in GW, let's say, the bubble, GG. I subtract the local part and I replace it by something presumably better. So now, of course, I have to tell you how to really get these presumably better quantities. Because what is the impurity model that I have here? So that means I have to come, in some sense, to a self-consistency. But you know how to do that, because you have already done that in DMFT just for this sigma impurity. We have just to extend it now to the 2 particle quantities. So let me put this up here. Well, what do you need to define an impurity model? Okay, Thomas knows something, but I don't hear to him. I don't listen to him, so who else knows how to define an impurity model? What do you need for this? You need some hybridization function, or equivalently, a Weiss field. That's essentially the same thing. Okay, and now, for the bosonic part, we will also need a U. And so this was dynamical, and this will be dynamical also now. So I need 2 functions, G0 and U, both dynamical, which together define my impurity model. I have shown you the action before, which was exactly of the same form of the actions that you have seen the whole week, except that we have made the interaction part dynamical. What do I do? So this defines my impurity model. And from this impurity model, I will calculate impurity quantities. So what will I calculate? G impurity, the Green's function of the impurity model. This is what you have been discussing, impurity solvers and so on. And also, and that is new now, I need the impurity screened interaction. How do I get that? I need to calculate something more, right? So to get that, for example, I can calculate the charge-charge correlation function of my impurity, and then I know that this is related by taking the bare interaction of the impurity, which is now the U, and screen it by this charge-charge fluctuations. So I can actually get an expression for this. Well, I can means numerically we can, and we will have to talk about impurity solvers. So Philip will say something about that tomorrow, I think, and I will also make some comments about some approximations at some point. So let's assume for the moment that we have techniques to calculate for this impurity model these two quantities. That means we also have actually the impurity self-energy and the impurity polarization. The self-energy, what is it? So that's actually the kind of final exam here for all the DMFT part, because you know all that, and we could check now. So sigma impurity. Yes, okay, you passed the exam. That is the Weiss field inverse minus the impurity Green's function inverse. And for the polarization, that's a little bit harder. So here we have to transcribe. But if you understood our translation between 1 and 2 particle quantities, here comes the bare interaction of the impurity and the screened one. And that is again this analogy of the two equations between 1 and 2 particle quantities. Okay. By the local charge fluctuation on the impurity, yes. So there's a notion of local and non-local screening. We will come back to that. Yeah. So this is really the processes here which live on the impurity. But you don't seem happy because you know that there are more processes, so we should have more, so we have to put them back. So how do we put them back? He complains. What do you say? So we need to come now to a point where we decide how to use these two quantities. Yes. So now you say the true self-energy, or the true in my framework of approximations, should be something where I have not only sigma impurity, but also these parts. So I should go into my self-consistency condition, and the self-consistency condition for the one particle quantity will otherwise be the same as in the DMFT, except that I don't only take this self-energy, but I take that one. Okay? So that means my self-consistency now, how will I write this? I will write it like this. My self-consistency will require that I take the non-interacting Green's function here. I subtract that self-energy, and that means I subtract both the GW non-local and the impurity one. So GW non-local means GW minus GW local again. And I take the inverse. That is then somehow an estimate for my Green's function. I take the local part, and this will be what I want to be my final local part of the Green's function to look like. Well, how do I succeed that my final local part of the Green's function will look like that? By using this expression in order to update the Weiss field. So that's as in the usual DMFT that you have studied. So that means I will use this for the Dyson equation by saying that my new G0 minus 1 will be G local minus 1 plus sigma impurity. And with this G, I will go back here. But here, I'm missing something, and I'm missing something really crucial. What am I missing? Well, I have to tell you also how I update this thing, right? And this thing has a Dyson-like equation here, this thing for two-particle quantities, that I should, in the same way as I use this for updating G0, use in order to update U. So my update should be U0 minus, U minus 1 equal W minus 1 local plus the polarization. But now I have a problem, because what is this? Okay, so now I need to decide at the same level as I decided what was G local, I have to decide what is W local. What do we suggest? Well, I should make the translation, and the translation will be that I use the Baer-Coulomb interaction, screen it by my polarization that I wrote here, minus P GW non-local, minus P impurity, and I sum it over Q, and that will give me the W local to update things here. Okay, so now my loop is complete. I have this impurity box here. I have to solve a dynamical impurity model with the quantities that I get here, supplemented by the non-local quantities stemming from GW. I will calculate the local parts of G and W and use those to update the auxiliary quantities to put in my impurity model. So now, this thing is the analog of the DMFT loop that you know. Right, okay. Write it like this. With the exception that I have supplemented it everywhere by a second line dealing with the two-particle degrees of freedom, or with these bosonic degrees of freedom, and that I have supplemented things here with non-local parts. So the non-local parts, I said they stem from GW. They show up only here for the moment in this loop. So now you can ask, can I get rid of this starting point dependence in GW? Can I self-consist also over this? And conceptually, the answer is yes, of course. I can iterate this cycle, then take my G and W and recalculate the GW quantities themselves. That means add an outer loop around this whole thing. And then converge this. And I think we are not going to converge this because I'm already over time, right? Yes. So that means we have coffee now, and we continue at this point tomorrow. Okay, thank you very much.